in this lecture we are going to discuss about the quantitative analysis by diffractions. In our last lecture we have discussed about the qualitative analysis by diffractions. Basically in our last lecture we have discussed about that suppose we are preparing any kind of materials. So, just to know the presence of that materials means what kind of materials are present inside that composites or maybe the alloys, we can get the informations. In this particular lecture we are going to discuss about the quantitative analysis, that means that what is the percentage of presence inside the matrix or maybe composites or maybe the alloys, that what kind of materials and what is the percentage of their presence. So, basically quantitative analysis refers to analysis in which the amount or concentration of an alloy or maybe analyte may be determined and expressed as a numerical value in appropriate units. Quantitative analysis is performed to accurately determine the concentration of elements, that what concentrations, whether it is 3 weight%, 5 weight% or maybe the 7 weight% or maybe so on in the material comprising a given sample. Generally quantitative analysis may be also be thought of in terms of the first is that precise determinations of crystal structure or maybe crystallite size and shape. Second is that determination of the phase proportions in multiphase samples. A variety of analysis techniques are used for metals and alloys to determine the alloy compositions of raw materials to verify the conformance of to a specifications or to identify the alloy used to make a specific components. Yes, sometimes as per our requirement or maybe as per our the requirement by any particular applications, we are preparing the new materials or maybe the new composites where we are adding numerous elements, and after that whatever the structure or maybe the whatever the quantity. So, if we are making it by ourselves we can easily get it, but if we are purchasing something or maybe we are getting some new materials. So, simple by these techniques we can calculate that what is the percentage present of that particular elements inside the matrix or maybe the composites. Diffraction patterns of polycrystalline materials are being used for phase quantifications. Diffraction methods have the advantage that the sample does not have to be disassociated or maybe you have to dissolve it or maybe otherwise changed, that means it is non-destructive in nature. So, before going to start, just let us know what is atom fractions and what is the weight fractions. So, atom fractions, so suppose before going to start just let us know that we are working on a multi component alloy containing the n elements. So, there are number of elements present. Weight fraction of the ith component is given by weight fraction of ith phase is equal to weight of ith phase by weight of first phase plus weight of second phase plus dot 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 up to weight of nth phase. When you are talking about the atomic fractions of the ith component, so generally it is equal to weight fraction of ith phase by atomic weight of ith phase by weight fraction of first phase by atomic weight of first phase plus dot 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 or maybe so on plus weight fraction of nth phase by atomic weight of nth phase. So, now we are going to discuss about the single phase quantitative analysis. So, generally we are doing it by the chemical analysis by parameter measurements. What are the basic principles? The lattice parameter of a binary solid solution of B in A depends only on the percentage of B in the alloy as long as the solution is unsaturated. Yes, of course, suppose I am making one kind of alloys or composites, so I am having one base materials and I am adding some constituents. The whatever the constituents I am adding, it should not go up to the saturation level. This principle is applied to perform the chemical analysis of binary alloys using their lattice parameter versus the composition curve, which can be established by measuring the lattice parameter of a series of previously analyzed alloys. This method has been used in diffusion studies to measure the change in concentration of a solutions with distance from the original interface. Its accuracy depends entirely on the slope of the parameter composition curve. In alpha brasses, just for example, which can contain from 0 to about 40% zinc in copper, an accuracy of plus minus 1% zinc can be achieved without any difficulty. So, now through different examples we are going to make you understand about the quantitative analysis. First, assume that two elements A and B are partially soluble in the solid state to form a single phase alpha. So, what is the procedure? Get the XRD patterns of series of alloys 1, 2, 3, 4, 5, 6 up to 7 with increasing weight percent of B. For sample 1, consider its peaks, find its 2 theta, D and corresponding HKL value. From D and HKL, calculate the lattice parameter of alpha knowing the crystal structure of the matrix. Then for sample 2 also follow the same procedure. Then plot the lattice parameter of alpha against alloy compositions, and from this plot the composition of alloy can be determined for a given lattice parameter. So, this is the whole procedure. These curves, if you see these curves, it is having two branches. One branch is from B to C, another is D to E. What does it mean? So, an inclined branch BC which shows how the parameter of alpha varies with the composition of alpha. You see, it is into the increasing order, and then after that it became a straight line. A horizontal branch DE which shows that the phase in alloys 6 and 7 is saturated because its lattice parameter does not change with change in alloy compositions. Say suppose I am adding one constituents or maybe the elements into the matrix. So, I will take 1%, 2 8%, 3 8%, 4 8% like that, and then after certain time the whole matrix will become saturated. That time if I am going to add more also, the lattice parameter is not going to be changed. This method is applicable only to binary alloys. In ternary solid solutions, the percentage of two components can be independently varied. The result is that two ternary solutions of quite different compositions can have the same lattice parameter. Now, if we are having the multiphase, then for multiphase what we have to do? What is the basic principle? The intensity of the diffraction pattern of a particular phase in a mixture of phases depends on the concentration of that phase in the mixture itself. The relation between intensity and concentrations is not generally linear because the diffracted intensity depends significantly on the absorption coefficient of the mixture, and this itself varies with the concentration itself. The exact expressions for the intensity diffracted by a single phase powder specimen in diffractometer is, so generally IHKL with this formula, where IHKL is the integrated intensity per unit length of diffraction line, A is the cross sectional area of incident beam, small r is the radius of diffractometer circle, m is the mass of electron, FHKL is the structure factor for reflection HKL, I0 is the intensity of incident beam, lambda is equal to wavelength of incident beam, E is the charge on electron, V is the volume of unit cell, mu is the linear absorption coefficient, e to the power minus 2m is the temperature factor, theta is of course Bragg's angle, and rho or maybe p is the multiplicity factor. So, when specimen in a mixture of two phases alpha and beta, then the intensity of the selected line of the alpha phase is I alpha HKL is equal to I alpha is equal to K1 C alpha by mu m, where K1 is the constant and it contains structure factor, multiplicity factor, Lorentz polarization factor, temperature factor and I0. The value of K1 is unknown because I0 is generally unknown, but this is unimportant if the ratio of I alpha to the intensity of some standard reference line is formed. Concentration of alpha can then be found from this ratio. Absorption coefficient mu m of the mixture is itself a fraction of C alpha and can have a large effect on the measured intensity, that is I alpha. Now, depending upon the type of reference line used, the three main methods of analysis are: first one is called the external standard method, means a line from pure. Second one is called the direct comparison method, a line from another phase in the mixture. Third is called the internal standard method, a line from a foreign material mixed with the specimen itself. Now, first what is external standard method? So, in this method experimental line intensity from the mixture is compared with a line from a pure phase. Relation between intensity ratio and phase concentrations is when X-rays encounter any form of matter, they are partly transmitted and partly absorbed, already we have gone through. Röntgen established that the fractional decrease in the intensity I of an X-ray beam as it passes through any homogeneous substance is proportional to the distance traversed x. So, minus d I by I is equal to mu dx, where the proportionality constant mu is called the linear absorption coefficient and is dependent on the substance considered, its density and the wavelength of the X-rays itself. Integration of above equations gives I x is equal to I 0 e to the power minus mu x. So, where I 0 is your intensity incident of the X-ray beam, I x is your intensity of transmitted beam after passing through a thickness x. The linear absorption coefficient mu is always direct proportional to rho, which means that the quantity mu by rho is a constant of the material and independent of its physical state, means either it may be solid or maybe the liquid or maybe the gas. Now, mass absorption coefficient of a substance, whether it is a mechanical mixture, a solutions or a chemical compound and in any state, is simply the weighted average of the mass absorption coefficient of its constituent elements. Therefore, mu m by rho m is equal to W alpha into mu by rho alpha plus W beta into mu by rho beta, or simply we can write the equations in this particular form. In terms of volume fractions, which is nothing but the I alpha is equal to K 1 C alpha by C alpha into mu alpha minus mu beta plus mu beta. In terms of weight fractions, so it is generally I alpha is equal to K 1 W alpha by rho alpha into second bracket W alpha into third bracket within first bracket, that is mu by rho alpha minus rho mu by rho beta, then third bracket closed plus first bracket mu by rho beta. So, for pure alpha phase I alpha p is equal to K 1 by mu alpha. Taking the ratio of intensities from pure versus given sample. So, I alpha by I alpha p is equal to W alpha into mu by rho alpha by W alpha into mu by rho alpha minus mu by rho beta plus mu by rho beta. This equation permits the quantitative analysis of two phase mixture, provided that the mass absorption coefficients of each phase are known. If they are not known, a calibration curve can be prepared by using mixtures of the known compositions. In each case, a specimen of pure alpha must be available as a reference material and the measurements of I alpha and I alpha p must be made under identical conditions. So, what is happening in this case? So, this side y is the IQ by IQP and the x axis is the weight fraction of quartz, that is in WQ. So, calibration curve, variations of intensity ratio with W alpha is for synthetic binary mixtures of powder quartz, cristobalite, beryllium oxide and the potassium chloride. So, with different weight fractions we are getting the different graphs. Next is the second one, that is direct comparison method. This method does not require a sample of the pure phase whose compositions is being determined. In this method, the experimental line intensity from the mixture is compared to a line from another phase in the mixture itself. The direct comparison method is of great interest because it can be applied directly to the polycrystalline aggregates. Most important applications, say suppose to determine the compositions of the mixture when the two phases have the same compositions but different crystal structure. Examples: measuring the amount of retained austenite in the hardened steel. The external standard method cannot be used because it is usually impossible to obtain a reference sample of pure austenite. Yes, of course, or of known austenite content of the same chemical compositions as the austenite in the unknown. Quantitative microscopic examinations is fairly satisfactory as long as the austenite content is fairly high, but becomes unreliable below about 15% austenite in many steels. In basic intensity equations, put K2 is equal to I0 minus A lambda cube by 32 pi r into mu 0 by 4 pi whole square e to the power 4 and by m square, and r value is this one. The diffracted intensity is given by I is equal to K2 r by 2 mu. So, simple, in this case we put the value of K2 and we put the value of r by 2 mu, where K2 is a constant independent of the kind and amount of the diffracting substance, and r depends on theta, HKL and the kind of substance. So, now we are going for to see the case study. So, number 1 case or maybe case number 1, number of phases in alloy 2 designated austenite by the subscript gamma and martensite by the subscript alpha. Above equations for a particular diffraction line of each phase becomes for austenite I gamma it is equal to K2 R gamma C gamma by 2 mu m, and for martensite I alpha is equal to K2 R alpha C alpha by 2 mu m. Taking ratio of intensities of alpha and gamma phases, we get I gamma by I alpha is equal to R gamma C gamma by R alpha C alpha. R values can be calculated from the knowledge of crystal structures and lattice parameters of both phases. Now, the value of C gamma by C alpha can be calculated from the measurement of I gamma I alpha and calculation of R gamma and R alpha. Once C gamma by C alpha is found, the value of C gamma can be obtained from the additional relationship, that is C gamma plus C alpha is equal to 1. Now, case number 2, number of phases in alloy, in this case is 3. So, if the steel contains a third phase, namely Fe3C, which is known as the cementite, the cementite concentration can also be determined by diffractions. In previous analysis, we have calculated the value of C gamma by C alpha from the following equations. So, by measuring IC, the integrated intensity of a particular cementite line, and calculating RC, C gamma by Cc can be obtained from the equations, that is I gamma by Ic is equal to R gamma C gamma by Rc Cc. Now, knowing the value of C gamma by C alpha and C gamma by Cc, C gamma can be obtained from the relations, that is C gamma plus C alpha plus Cc is equal to 1. Other analytical problems to which the direct comparison method has been applied are determinations of mixed iron oxide in the oxide scale on steel, determinations of beta phase in titanium alloys, and determination of uranium and plutonium in mixed carbides. Precautions in direct comparison method: in choosing diffraction lines to measure, overlapping or closely adjacent lines from different phases must be avoided. While chromium radiation is the most popular, shorter wavelengths such as Fe K alpha or maybe cobalt K alpha and molybdenum K alpha will increase the number of lines on the pattern and thus provide more measurable pairs. Specimen preparations involves wet grinding to remove the surface layer, which may be decarburized or otherwise non-representative of the bulk of the specimen, followed by standard metallographic polishing and etching. In grinding and polishing, care should be taken not to produce excessive heat or plastic deformations, otherwise material structure will be changed, which could cause partial decompositions of both the martensite and austenite. In the measurement of diffraction line intensity, it is essential that the integrated intensity, not the maximum intensity, be measured. Now, the third one, that is called the internal standard method. In this method, a diffraction line from the phase being determined is compared with a line from a standard substance mixed with the sample in known proportions. Applications of the internal standard method: suppose the amount of phase A must be determined in a mixture of phases A, B, C or maybe so on, where the relative amounts of the other phases present like B, C, D, E so on may vary from sample to sample. With a known amount of original samples, mix a known amount of standard substance S to form a new composite sample. Let Ca and C prime A be the volume fraction of phase A in the original and composite samples respectively, and let Cs be the volume fraction of S in the composite samples. Intensity of a particular line from phase A in diffraction pattern prepared from composite sample is given by Ia is equal to K3 C prime A by mu m. Intensity of particular line from standard S is equal to Is is equal to K4 Cs by mu m. Taking ratio of Ia and Is, so simple Ia by Is we will get K3 C prime A by K4 Cs. Note that mu m, the linear absorption coefficient of the mixture, and unknown quantity drops out. Physically, this means that variations in absorptions due to variations in the relative amount of B, C, D and so on have no effect on the ratio Ia by Is, since they affect Ia and Is in the same proportions. Volume fraction of phase A in composite sample we can calculate by this formula. Volume fraction of phase S in composite samples we can calculate by this formula. Now, taking ratio of Ca prime and Cs, we have Ca prime by Cs is equal to Wa prime rho S by rho A Ws. Substituting for C prime A by Cs, we get simple Ia by Is is equal to K3 Wa prime rho S by K4 rho A Ws is equal to K5 W prime A, and Ia by Is is equal to K5 W prime A, where K5 is equal to K3 rho S by K4 rho A Ws is constant if Ws is kept constant in all the composite samples. The relation between weight fraction of A in the original and composite sample is W prime A is equal to Wa into 1 minus Ws. Now, we can write Ia by Is is equal to K5 W prime A is equal to K5 Wa into 1 minus Ws. So, simple we are substituting this one over here, which is nothing but the K6 Wa. So, Ws is always the constant. The intensity ratio of a line from phase A and line from the standard S is therefore a linear fraction of Wa, the weight fraction of A in the original sample. Now, we are going to give you the more clarity by giving an example. Say suppose measurement of the quartz content in industrial dusts. So, what are the steps? First, make a set of samples containing known concentrations of quartz and constant concentrations of a suitable standard fluoride. Quartz and calcium carbonate are mixed in known compositions. Add enough fluoride in each mixture to make the weight fraction of fluoride in each composite samples equal to 0.20. Next, second step, prepare a calibration curve from the following intensity measurements on these synthetic samples, like Iq is equal to intensity of the D is equal to 3.34 angstrom line of quartz, and If intensity of the D where is equal to 3.16 angstrom line of fluoride. Measure the ratio Iq by Is for a composite sample containing the unknown and the same proportions of standard as was used in the calibrations. Knowing the value of Iq by Is, weight fraction of quartz can be obtained from the calibration curve. So, I am getting this point and this point. So, internal standard of fluoride means calcium fluoride, generally we are taking. So, Iq by If into the y axis, weight fraction of quartz is into the x axis. Now, what are the other applications? So, generally analysis of the cement we can do by these methods, analysis of clay minerals we can do by this method, determination of chrysotile asbestos in airborne dust also can be done by these methods. Of course, there is some other methods also, that is called RIR or maybe the reference intensity ratio method, another one is called the Rietveld method, or maybe other way we can say it as a whole pattern analysis. So, what is RIR or maybe the reference intensity ratio method? The RIR method is based upon scaling all diffraction data to the diffraction of standard reference materials. The reference intensity ratio is a general instrument independent constant for use in quantitative phase analysis by the X-ray powder diffraction internal standard method. The ICDD has generalized the internal standard method by comparing the strongest line of the pattern of a large number of substances with the strongest line from a single standard reference material. The standard reference materials chosen was alpha Al2O3, a synthetic corundum commercially available as Linde A powder. Reference intensity ratio for a substance is defined as the ratio of maximum intensity of the strongest line from the substance to the same quantity from the corundum determined from a mixture of equal parts by weight of the substance and the corundum. That means, I by I corundum is equal to maximum intensity of the strongest line from the substance by maximum intensity of the strongest line from the corundum. These values are available in the powder diffraction file for many phases. The weight fraction of A in the unknown is given simply by 1/2 or the ratio of IA by I corundum for the unknown corundum mixture to the tabulated value IA by I corundum for the A corundum mixture. So, WA unknown is equal to half into IA by IC unknown corundum mixture by IA by IC A corundum mixture. So, where this first is the corundum mixture, this one is the intensity ratio for A corundum equiweight mixture from powder diffraction files, and this one is here that intensity ratio for unknown corundum equiweight mixture from the observed data. Second is called the Rietveld method or maybe the whole pattern analysis method. So, generally Rietveld refinement is a technique devised by Hugo Rietveld. In his name just we are calling it as a Rietveld method, who has invented this method for crystalline materials. If a diagnostic peak overlaps another peak, then extraction of its intensity can be uncertain. If the whole quantitative analysis hangs on this peak intensity, then the uncertainty propagates. On the other hand, if the whole pattern is fitted, then all the available information is being used and success does not rest on the measurement of just 1 or 2 peaks. This method uses least square approach to refine a theoretical line profile until it matches the observed profile. Very useful in cases of overlapped reflections, multiple phases and complex structures. The principle of the Rietveld method is to minimize the residual function, that is WSS, using a nonlinear least squares algorithm. So, what is WSS? Is equal to summation over I, Wi second bracket I experimental minus I calculated whole square. So, where Wi is equal to 1 by I exponential. I exponential observed intensity at the ith steps, I calculated is the calculated intensity at the ith step. How we are going to calculate the intensity? So, generally I calculated, we are following these whole equations, where this is known as the scale factor, then we are having the Lorentz polarization factor, then we are having the structure factor, then we are having the profile shape functions or maybe the preferred orientation factor, then we are having the absorption factor, and then we are having the background function. So, like this way we can easily calculate. So, how we are going to calculate the intensity calculations? That is, by this formula. So, we are having that scale factor, we are having that Lorentz polarization factor, we are having the structure factor, we are having the profile shape functions, we are having the preferred orientation factor over there, then we are having the absorption factor, and then we are having the background function. The relative weight fraction of phase alpha, that is W alpha in a mixture of n phases, is given by W alpha is equal to S alpha into ZMV alpha by summation over I is equal to 1 to n SI ZMVI, where S is the Rietveld scale factor, Z is the number of formula units per cell, M is equal to mass of the formula unit in atomic mass units, and V is the unit cell volume in angstrom cube. So, Rietveld procedure, first how to do that? First, choose the appropriate software program. There are so many softwares by generally which we can do the Rietveld method, that is the Expert High Scores Plus, GSAS, Raytan, Mod Program, Full Prof, Topaz and BGMN. Then second, load or input the phases in the sample obtained from qualitative analysis. Then third, adjust manually some parameters like cell intensities, background. 4, refine overall intensities and background, peaks positions, peak shapes and structures, and the fifth, assess the results. Of course, now there are certain practical difficulties generally what we are getting at the time of doing the quantitative analysis. So, factors causing difficulty in quantitative analysis are, first one is called the preferred orientation. What is that? The basic intensity equations is derived on the premise of random orientations of the constituent crystals in the sample and is not valid if any preferred orientations, that means texture, exists. Two approaches are used to minimize the error in the presence of texture. One is called the averaging intensities. If certain lines from a substance are abnormally weak because of texture, then other lines will be abnormally strong. Only by measuring all the lines and averaging them in a particular way is valid data obtained. The number of diffraction lines required for the analysis increases with the degree of texture. For strongly textured materials, molybdenum K alpha radiations is needed to provide the enough lines. Second is that averaging orientations. The specimen is rotated in particular ways during the measurement of line intensity in order to present more crystal orientations to the incident beam. Next is called the microabsorption. Microabsorption causes loss of intensity inside a particle. If this loss is different between two phases, the beam is interacting with different phase volumes, thus the QPA results will be falsified. Microabsorption occurs in samples with large particles and phases with large differences in absorption coefficients. This is because the effect of microabsorption in each diffracting crystals is not included in the basic intensity equations. The microabsorption effect is negligible when all phases have the similar absorption coefficients and same particle size, or when the particle size of all phases is very small. Next, last one is called the extinction. This effect produces a reduction in diffracted intensity as a crystal becomes more nearly perfect. Usually the crystal is imperfect, but not ideally imperfect, and hence the measured intensity is somewhat less than the value predicted by the basic intensity equations, which is derived for the ideally imperfect crystals. So, now we have reached up to the last slide of this particular lecture. So, just we are going to summarize the whole lecture. So, first in this lecture we have discussed about the X-ray diffractions is used for the quantitative phase analysis of multi-phase materials and have lesser uncertainty than other methods. Depending upon the reference line used for comparison for phase quantifications, three main methods of analysis are internal, external and direct comparison method. RIR method is the standardizations of the internal standard method for many substances with respect to a standard reference. Reed-Bell method is a whole pattern analysis method and have better accuracy than single peak methods. Thank you.